This is the first of a two-part video on speeds and feeds, so we're going to take you through this quick. In this lesson, you're going to look at different cutting tools, definitions of speeds and feeds, calculating cutting speeds and feed rates, and then just get a little bit of practice for how to do that before your assignment. So first is basic cutting tools. These are some different milling bits. This is a end mill bit, and it has two flutes. There's two cutting teeth here. This is a ball mill because it has a rounded edge, and it also has two flutes or two teeth. And this is a non-center cutting end mill. It has four flutes or four teeth, and you can see the difference between this one on the right and the one on the left is this one has a hole in the middle of it. And those are the three that we're going to take a look at. We do not have an indexable shell mill that we're going to use, so we're going to pass on that one. Here's another example of one: combination drill countersink. This extra angle here gives it a countersunk, so it drills a hole and then it widens that hole right at the top so that a screw head will fit in there really nice. A spotting drill to drill straight down, and then another countersink drill, just a little different than this one. So, information about flutes. You might want to even take a screenshot of this and add this part to your notes. This is a two-flute end mill, because you're going to see a picture like this, almost exactly like these on the final. Two flutes have more room for chip evacuation, so these are pretty significant pieces to note. They're used for lighter metals, but they are weak. They have a shorter tool life, and weak is relative because they're still pretty strong, but two teeth is weaker than four. A four-flute end mill has more cutting edges, so it has a longer tool life. It has twice as many. It can be used for harder metals, but it can also clog easily in deep cuts, so you can't cut as deep with a four-flute end mill. So looking at center versus non-center cutting, a non-center cutting has this hole in the middle, and if you're doing a non-center cutting, here's an example of a end mill, and I have a block right here. So if you're doing a center cutting, which is the middle one here, you can plunge straight down into it. With a non-center cutting, if you plunge straight down into it, then that center hole will get clogged and the bit could get too hot, it could crack. So for those, you have to kind of come in at an angle for those. We actually don't have any non-center cutting so that we don't put ourselves at risk for cracking bits. So here's some examples of some tools. This is a 1/4 inch, two-flute, HSS means high-strength steel, single end mill, and it's used for cutting aluminum. It has a 3/8 inch shank, which is this piece down here, and a 1 1/4 inch cutting length. And that's important because if I have this bit here and I want to cut 2 inches down into something, maybe I'm trying to cut this direction and I'm trying to cut this deep, I can't do it because the shank length is not long enough. So knowing the shank length and how deep you want to cut is important. Then this other one here is a 1/4 inch two-flute ball mill. So these would just be typical descriptions that you might see. Another one here is a countersink tool. It's also used for engraving, and we have one of those. And then a combined drill and countersink. So I'm going to show you the bits that we have just before we watch this video. We have these two tools. This one here is an end mill, and you can see it has two flutes or two teeth. This one here is a ball mill. It has a curved surface on the top. It has four flutes or four teeth. So this one is used for nice curved surfaces like this because it's not going to give scratchy lines on there from these sharp edges. One other thing to note that's different is these spiral in opposite directions. This one here will pull material up and out of the block. This one actually pushes material down into the block. So when you're milling your box, it's pushing material down into the block, and what that does is it makes a really nice clean edge so you don't have to deburr that or sand off those fine wood grains that kind of stick up out of there. So those are two tools that you end up using. The third tool, which is actually the one you're going to start with, is used on yo-yos that you're going to mill. So you'll have a yo-yo, and you can see this has got one sharp point here. It actually only has one tooth because it only has one edge that you're cutting on. And it's shaped like a V, so the further down that you press is the deeper of your engraving line. Here's an example of a yo-yo that was engraved. I can show you this in person if you want to see. So it spins and it ends up carving out whatever it is that you're trying to engrave. So we'll go ahead and start this video, and this shows you some milling with metals, which is actually pretty cool.
The main objective in the selection and application of cutting tools is to safely machine a workpiece in the shortest possible time while meeting the part's quality requirements. There is no ideal cutting tool material, but the rapid evolution of tool materials has given us a wide choice to meet any need. High-speed steel tools are commonly used in tool rooms and in low-speed operations. Round tools such as drills, taps, and end mills are commonly made of high-speed steel. Coatings have extended the applications and cutting life of high-speed steel tools. Carbide tools, particularly coated carbides, are today's most common cutting tool material. There are a great variety of carbide compositions and coating types. Carbide tools may be indexable inserts or solid round tools such as small diameter end mills or drills. Coated carbide inserts are the first tool material to consider for most production operations. Most insert coatings have multiple layers to protect the tool against abrasion and chemical wear. Ceramic inserts may be alumina-based or silicon nitride-based. They withstand higher heat than carbide, have good resistance to abrasion, and they cut very fast. But ceramic inserts are less shock resistant than carbide tools, so their applications are limited. Cermets are composed of titanium carbide or titanium nitride with excellent resistance to various forms of wear. But cermets do not withstand high heat well. The super hard materials are cubic boron nitride, CBN, for ferrous applications, and polycrystalline diamond, or PCD, for non-ferrous applications. Both materials are expensive, but can outlast carbides by 10 to 100 times.
Green Sally up, green Sally down.